Machine learning is something that can be perceived as complex. Jomit is here to tell us everything you need to know if you're in the industrial IoT space about machine learning, where it's used, when to use it, how to use it. That's today on the IoT Show. Hi everyone, this is the IoT Show. I'm Olivier, your host. Thanks for watching. Today we'll talk about machine learning in industrial IoT. And for that we have Jomit with us. Jomit, how are you?
I am good, Olivier. How are you?
I'm great, fantastic. Thanks for joining us in the studios. I was saying that we have these configurations of people being online and it's always weird. Much better to have people
Absolutely
in the same room. I appreciate that. So you're here to tell us about ML. Demystify machine learning for IoT developers, architects, and others. But before we jump into that topic, who is Jomit? What are you doing at Microsoft?
Okay, so my name is Jomit Waghela. I am a principal PM in our Edge and Platform Engineering team. My focus is to work with customers, some of our large strategic customers, in manufacturing as well, of course, and help them design good solutions around industrial IoT, and also focus on machine learning as well.
Awesome. And you've been building some samples. We'll talk about them. We'll go through them. My background is IoT development, embedded devices, more and more cloud, but initially more devices. And so machine learning is something that very often I'm looking at, scratching my head and saying it's kind of like black magic, just works. But we'll see today it's not the case.
Yes.
But before jumping to that, tell me a bit about what kind of scenarios, to ground things into reality, what kind of scenarios do benefit from using machine learning, especially in industrial IoT?
Yeah, sure. So I've been doing manufacturing or working with a lot of our manufacturing customers for almost like 7 years. One of the things I've seen is that there are two general themes for manufacturers. One is they want to know what their processes are doing right now, which is more near real time. So it's like a visibility. And then the second theme is around how do you optimize those processes, right? So how do you make sure that there is less waste? How do you make sure that you can improve your yield overall for the manufacturing? And the machine learning generally falls into the second category. How do you optimize your processes so that you improve your yield, right? So some of the common use cases is how do you detect anomalies when there is around downtime of your machine, so things like that. That would be like the basic scenario. Then you would go around how do you predict stuff for things like when is the machine going to go down? That's a predictive maintenance, very classic use case. But it also goes beyond how do you augment some of the human efforts around, let's say, quality inspection or managing inventory or things like that. How do you automate that, help the operators and people in the plants make better decisions using the predictions from machine learning? So that's kind of the general use cases. And then it goes beyond the factory floor, so things like forecasting your sales, forecasting orders, forecasting your shipments. So it goes the entire spectrum of it.
Yeah, got it. Okay, so you're going to walk us through the principles and how it's done, right? So let's think about scenarios such as anomaly detection. We've seen demos, of a camera showing a conveyor belt with electronics in there, and then suddenly there's, an alarm that says that piece of thing is faulty, right? And it's black magic, that's what we're saying, right? So what is the process to get there?
Yeah. So I think part of my goal is to make sure that it's not a black magic, right? So open up that black box and explain to everyone, especially the IoT developers. So generally, I started my data science before like 4 years when customers keep on asking about this as a scenario. And I myself have been learning this. I was an IoT person, I was an app dev person. I started learning machine learning in data science before 4 years. And so that's kind of my general message. If I can do it, anybody can do it.
Fair enough.
Generally, there are like 3 phases of machine learning. So the first phase is what we call exploration, explore. The second phase is experimentation. And the third phase is operation, which is operate, right? So that's what we call explore, experiment, and operate. And we'll dig a little bit deeper on what are the different steps and tools that we have available today, which were not available 5 years back, frankly. And so it will be harder for you to do machine learning. But today, it will be much easier for you to do that.
So you put together a blog post that explains these 3 main aspects of machine learning and their applications in industrial IoT. So can you walk us through that real quick?
Sure, definitely, right? And I think, so this is the blog post. And of course, the title is Demystifying Machine Learning for Industrial IoT. And essentially what I talk about here is those 3 phases that we talked about, but also individually, what are the tools and outputs for each of them, right? So for example, on the explore phase, what you're looking for essentially is validating whether machine learning is the right approach to solve that business problem, right? It's very critical before you jump on to experimentation. In the experiment phase, you're trying to map whether you identify that your machine learning is a good kind of way to solve the problem. Now, how do you align the machine learning output with what your business objective is, right? There's generally like a saying in machine learning, like all models are wrong, some are useful. What that means is most of these machine learning models, they output in probabilities, right? No model is 100% right? So now if your model is 80% or 90% of the time of the right, how do you now then map it to, let's say, if you want to reduce scrap or you want to improve yield by X percentage, how do you map to that? That's the experimentation phase.
Okay, got it.
And then the last phase, which is operate, is where you look at how your plant operators or whoever is using your machine learning model, how are they making business decisions day to day, right? Are they going to make a decision to stop the line, right? Or are they going to make a decision to send somebody, take a flight to repair something?
Yep.
You may want to go and look at how these decisions are made, whether it's on the plant or on the cloud, things like that. So that's what we try to work out and deploy the actual models in general.
And is it fair to say that the cycle continues, right? Because it's not because you have a model that is deployed that it's static. You actually will try and optimize it and change it based on all the data you will gather along time or across different locations. You'll be able to enhance these models to get better results, lower priority of false or things like that, right?
Yeah, absolutely. Yeah, I mean that's a critical. And in fact, first few models would not be a good model for you anyway, right? Because you may not have all the data yet. So this whole explore, experiment, and operate, it's like a cycle that keeps on going, right? Yep. And you may need to do all this again and again. And that's why the importance of automation comes in, right? And we'll talk about that a little bit.
Yep.
It's how to automate that pipeline so that you can just pass in a parameter and do all these things automatically as well.
Let's start exploring then.
Okay, awesome. Okay, so before we explore, so the first thing we need to do is understand what the business problem is, right? So for our scenario, what we are talking about is how do you actually go and reduce scrap, right? That is our kind of scenario, right? Okay. So generally manufacturers, they produce a bunch of things, they have some X percentage of scrap rate, right? So think of it as if you have a 10% scrap rate, which means that 10% of your production is going in scrap and rework. Now you want to reduce from that 10% to let's say 5% or 8%, right? How do you gain that 5% or 2% less, right? That is kind of our scenario here. You also need to map your scenario with your business impact, right? So map it, okay, 5% less scrap equal to how much dollars of savings, so things like that, right? That's important as well. So in our scenario, that's exactly what we're going to do. The way we are trying to look at is what are the top factors which are causing the scrap, and in our process or in this existing scenario, the quality of the output is predicted every 24 hours.
Okay.
So what we want to do is we want to predict that quality before that, right? Before a human or a quality inspector inspects it, we want to predict whether this is going to be a good quality or not, and it will help us understand things a little bit better, and also identify what factors are causing it. Now, there could be various external, internal factors that could affect it. Like, for example, you could have a bad raw material from a supplier that could affect your entire thing. But I think what we are limiting here for this experimentation is we are looking at the sensors which are on our assembly lines. Okay, and those sensors are giving us input of what was the value when this product was manufactured. Right? Okay, and then there's another system which is a quality management system, which is a database where a quality manager would log the quality output as a separate system. So these are the two systems we are taking into account. But in the real world scenario, you will have more data points from other systems as well. Right? So this is the general design that we are following here. Now, of course, this is kind of one aspect of the sample thing. So what we are trying to do here is we have two different sensors, right? One is our OPC UA server that's sending us a bunch of temperature and humidity sensors. And we also have other external sensors that we are simulating. And we have roughly around 41 different sensors that we are simulating. All this data is going to our IoT hub, which is our flagship sort of IoT ingestion service. And then ultimately, we are storing this into a data explorer, right? And I'll talk about what data explorer is and everything. But essentially, it's sort of like a big data storage for IoT workloads. And then what we'll do is we'll get that near real-time data in our Azure Machine Learning service, and then do some modeling predictions on top of it, save those predictions into a SQL database, and then we'll do a Power BI dashboard to make sure how our model is performing. So that's kind of the general,
pretty straightforward,
pretty straightforward architecture that we're going to do.
And you were saying we're leveraging sensors that are already existing. Actually, you don't have to decide you're going to do machine learning and then install the sensors. Like to operate these machines, there are sensors already existing there. What you're trying to do is optimize the process here.
Exactly, yeah. And most of the IoT is always brownfield, right? There's always sensors, there are always lines there. And so what you're doing is you are taking that data, and now the work starts on how do you prepare that data to be ready for machine learning, right? So that's what we're going to focus on next. Okay, so that's kind of the design. Now let's go to the first step, right? Let's look at the Data Explorer and see what the data sort of looks like.
Okay.
So for people who are new to Data Explorer, as I said, Data Explorer is a big data sort of analytics service for IoT data. It can store large amount of data, and you can do a good sort of querying and database stuff on top of it. Right?
Time series data.
Time series data.
Time series data,
well.
right?
Yeah,
Super important.
Yeah, exactly. Okay, so this is our data, and this is our table that we have. So I can just run the query, and as all databases, there is a query language here. The specific query language that Data Explorer uses is called KQL.
Okay.
It's very similar to SQL. I think the nice thing about KQL is it gives IntelliSense and everything, so it's much easier for people to learn the querying and do all the joints and everything around it. Okay, so here we can see that there are roughly around kind of 16 million data points here, which I just started before a couple of weeks. So right now, this table, which is the OPC-UA raw, it's a raw table that stores all the raw data. So we have data coming from the OPC-UA server, which has this kind of a message format. But what we are interested in right now is the data is the sensor data, right? So we can run this, look at this sensor data here, and this is the data that we will be kind of playing around. So these are basically like a JSON file. This data has a batch number linked to it, and there are roughly around kind of 41 different sensors to look at. Okay. So that's kind of the first step, which is we look at the data, it's there, and all the data we can see it. So now we start going to the machine learning one. Okay. So the service that we generally use for machine learning is what you call the machine learning workspace. So when you create a workspace, you would get your own sort of user experience, and it includes all the services and tools that you need to do anything and everything around machine learning. It's like one-stop shop. Everything is there for you. Right? That's the machine learning studio. And what we'll try, for most of the experimentation, you would want to create a basic flow of how you write the code and how do you do all these things. And I think the best way of doing that is creating a notebook.
Okay.
Right? So what's a notebook? You can write your Python code in a notebook in a more interactive way, right? So you can write the code, you can run the code, compile the code, debug code, visualize the stuff like graphs and things like that, and also document stuff all in one single file. So that's kind of the nice thing about sort of notebooks, right? And so if people are new, I can just quickly show them what notebooks are. So when you go in your studio, you'll have these notebooks. You can click on this plus, click on a new file, and then just create a new notebook here. So I'm just going to create a new notebook called demo. And most of the times when you create these kind of notebooks, you would be all linked with a compute, which is kind of comes with it. If you don't have a compute, you can create a managed compute which installs all the dependencies that you need for it. So it's sort of like your cloud workstation where all the software is installed for you and you just start developing, right?
One thing important with the notebooks is that it's a let's say a playground for different types of people to interact and work together in, right? It's not just a data scientist or an engineer or a developer. It's someplace I'm pretty amazed when I look at these notebooks because it talks the language of a developer. The data scientist is comfortable with it, and so sometimes engineers who are professional in a specific area of the industry, manufacturing, whatnot. There might be mechanical engineer, chemical engineer. They still understand what's going on, and so you have a collaboration that's happening around these notebooks. It is pretty amazing, actually.
Yeah, absolutely. And then the industry has started adopting notebooks in pretty much all the spaces that you talked about, right? Even data engineers and data scientists and developers, everyone is starting to use these notebooks as a one way to do development and interaction as well. So this is a simple thing. You when you create a notebook, you get attached with your compute, and then you can start writing your code here, right? So I'm just going to say hello here. And the nice thing is you can actually, each of these are kind of cells that you can type in, and then you can just run individual cells and look at the output that comes out of it. It's a very simple thing.
And then you can attach, like, you have a bunch of libraries, existing packages that you can add that do these various steps, in your pipelines, right?
Yeah, exactly. So those are the Python packages, right? So all the Python packages are available to go and do all this analysis. Let's look at that, right? So the next step, what we'll do is we'll actually go into the exploration part, right? So the first step we'll do is try to look at those two data sets that we had, which is the data set that's coming from our real-time sensors, and then the quality data set, which was part of the other system. What we'll do in this step is merge those two data sets and create our final kind of raw data set so that we can actually do some more analysis on top of it. Okay.
Sounds good.
Now, the good thing here is that in notebooks, you don't have to go and kind of stage data anywhere else. You can directly go from notebooks, connect to your data explorer directly and get the data. So this is a package, as you told. There is a KQL Magic as a Python package. You install that package. And by the way, all these notebooks and all the code is available on our GitHub. So you don't need to worry about if you're not kind of following it.
We'll bring the link at the end.
Yeah, we'll bring the link at the end. Okay, so here is kind of the query. So this is our same query that we can run on top of our data explorer that you can actually go and run here. This is the nice thing, right? So you're writing the same query. You're not writing any sort of Python conversion stuff here.
Nice.
And once you get this data, so this is the sensor data that we are getting. So you can see that the columns here are all the 41 sensors.
Okay.
Now what we can do is we can also get our quality data. So what we have done is for now exported the data from the local database and created like an exported CSV and put it in our data lake. So that's the thing.
Okay.
So this is our kind of batch quality data. So what this data has, I think we have trimmed down a lot of things. So all this has is two columns. One is quality, that was the 0 and 1, and the batch number, right?
Okay.
So 0 means it's not a good quality, 1 means it's a good quality.
Binary.
I mean, it's a binary simple thing.
Yeah.
In real world, you might have different enumerations of what the 0, 1, 2, 3, 4 means, right? We are trying to make it more simple.
But actually super common in manufacturing world to have 0, 1, because if something is not of quality, it's just like, it's just dumped, right?
Yeah,
you don't keep it.
Yeah. I mean, you can make it simple, or you can have a nuanced calculation where there are different stages of rework, and you can have this in there.
Yeah.
But this is a simple thing. So here, what happens is that our telemetry sensor data has a batch number. Our quality data has a batch number.
Okay.
So those are the two.
Correlate like
that's
that.
how
Okay.
we're going to join both them together exactly. Now, in a lot of scenarios, you may not have this data, and you can use a timestamp, right? You can say, okay, fine, between these timestamp, this time, and then join them as well, right? But we want to make things easier. Okay, so we're using this batch number, joining this data, so which means that now for each of the rows, what we have is we now have the actual quality. So you can say at the end, we now have the quality column here that we can kind of join. Okay, so at this point in time, we have now our raw data set ready. Now, the most important thing in machine learning would be to register your data and version your data.
Okay.
So a lot of times when, for the application developer, versioning the code is an important thing. In machine learning, versioning your data set is the most important thing. Why? Because your data reveals the patterns on which the model is built. When your data changes, the pattern changes, which means your model could change. Which means that it's important that you version your data and you link it back to what your model is and say, okay, fine, this model version is linked with this data version. Because as soon as your data changes, your model will definitely change. Right? So those are the important thing. And machine learning sort of workspace provides the same thing. So what we have done is we actually register this data set. So what we can do is quickly go and look at this data. So this is kind of our data set. And you can see it's kind of versioned here as well, right? And so later on, if somebody wants to actually go and look at this data, they can actually click on this data and click on Explore, and you'll pretty much see the same format of your data with all the sort of the 40 columns in here. That's the real data. Right? So that's the step one, right? You go and merge this data set, version data set, put it in there.
One thing I want to mention right here, at the very beginning, you mentioned how many data points you had to start with, and here you're doing click, 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 and boom, things appear immediately, and your queries are going super fast.
Yeah,
It's something
exactly.
important because you're working. You should not go drink coffee each time you click on, run that query to get the data.
Yes.
Everything happens for you super fast.
Exactly,
right?
and you're going right to the source, right? So Data Explorer is right to your time series data store, which has live data.
Yep.
And you can go directly to that store and get the live data as well, right? So there's no intermediate
Brilliant.
here. Okay, perfect. Okay, so the next thing, what we'll do is we will do something called exploratory data analysis. This is kind of a mouthful of a term. It's called EDA.
Okay.
What we are doing here is trying to identify what are the patterns in the data, and there are some techniques, and we'll talk about that. And at the end, we have to determine that out of those 41 sensors that we had, that we are trying to go, which are the ones which are most likely or good for predicting the actual quality. Because not all sensors will be good, right? Some sensors may have the same data for all the time, and they're not good, and we can eliminate them.
Well, then they're not good. Doesn't mean that they don't have valuable telemetry for your operations. Where you're saying that they don't have valuable information for detecting the anomaly that we're looking for, right?
Exactly. So that's the experiment that we're trying to do. So in this specific experiment, maybe they are not valuable. You could create a different experiment, and they will be valuable for them. Yep, exactly. Okay, so this is where our raw data set that we versioned would be very helpful now. So that's the data set that is going to be our base for the next, all the steps, right? So now we're going to use that data set. So we don't have to go back to Data Explorer and do all these things. We just go back to now our version data set. And typically you can provide a version number, but if you don't provide a version number, it gets the latest data from you. Okay, so the first thing we do, and this I'll not go through every step of them. You can look at the notebook in the GitHub repo. But for example, the most kind of common thing would be how many data points are missing in your entire data set that you kind of capture, right? So we captured for a 5-hour time period of the data from the historical. And we looked at it and we said, okay, for this sensor, which is S4, 70% of the data is missing, right? Which means that there is null values in that. Okay. So we can go back and debug why this is null, but that's good. But for this experiment, what we will say that, okay, fine, if this much data is missing, we probably don't need to use this for now, right?
It can actually make the model not working worse, right?
Yeah, exactly. Because there are a lot of null values, and we don't want to just hypothesize and put some random values. Okay, so this is the one kind of thing where you do the missing values, and you can eliminate some of those things. The second thing would be to look at sort of outliers, right? So outliers would be like, there would be some sensor mean max that most of the PLCs and everyone, they would set the range of it, right? Sometimes your values would go above or below that range, right? That's what we call anomalies. But if the anomalies are happening more than usual, that means it becomes not normal, right? But what we are trying to say is that if there is a range and there is an anomaly, we don't want to create an average out of it, because then that anomaly would cause the average to be very bad of the entire thing, right? So we look at the anomalies, look at the outliers, and then we either remove those data points or we look at it and say, okay, fine, this entire sensor is a lot of fluctuations.
Yes.
We can remove that entire sensor out of it, right?
Yeah,
so that's kind of the outlier analysis that we can do out of it. And then the last, which is, I would say one of the most important thing, is to do what we call correlation analysis, right? So if you look at this graph here, it may be kind of handful, a little bit confusing to do, but the core kind of concept around correlation is trying to look at each sensor and comparing with other sensors, right? So all the 41 sensors compared with the other 41, and see which ones are positively or negatively correlated in terms of values of each other, right? So here in this chart, what we're looking for is which are the most kind of black, dark here, and which are the most light ones, right? And what we try to do is we try to look at what are the top positive and the top negative ones, and we pick those sensors first as our experiment, right? This is generally kind of a good thing to do instead of doing all the sensors in there. So what we have done is that in this scenario, we identify what are the top ones. So out of all the 40 ones, these are the ones that we selected, right? So here are the top positive ones and the top negative ones. And then I think it's important that once we have that, we again registered our new data set with the version, because remember there was the old data set with raw, but now we have the narrow one with only the 15 sensors that we need.
The cleaned up one.
Exactly.
That's what you mean when we mean cleaning the data.
Yes.
That's this exploration phase of deciding what you're going to keep, what you're going to set aside, and that's a human doing that, right?
Yes. So a lot of times I think it's a human doing that, but I think now with these tools and everything, you can just write a one-line code and then it will just do all these things for you and visualize it. Okay, so now we're going to save it into the feature data set. This is again the same data set. I can go back and we can quickly look at it. So if you go back in the data, you will see that now we also have our feature data set, and there's the version 1 of it, right? Okay, so we want to make sure that's kind of the step point. Okay, so that's the second step done. So now we have our actual data set that we can start doing some modeling around.
Okay.
Now, before we start doing modeling, there's one aspect that I think a lot of times for IoT kind of developers is very important, which is frequency analysis, right? Which I think a lot of IoT developers may have already heard of. So where can frequency analysis be helpful in machine learning, right? So think of it as currently we are in this scenario, we are getting the data points every 2 seconds. So the sensor is coming out and sending me every 2 seconds the one value. Now, what if that sensor is not giving me good output, but what if I change the frequency to 1 second, one value every second instead of 2 seconds, right? Then in that scenario, I may get more data points, which means that maybe my model might be good, right? But how do you analyze what is the right frequency? Is it every 2 seconds, 1 second, or every like 10 values or 10 hertz per second, right? So frequency analysis can help you kind of very quickly sort of do that. So this is a sample that we have in the notebook where you can look at the sensors and plug it into this basic sort of Nyquist sampling theorem. A lot of times the OT teams, and I think in they use Excel to kind of do all these things as well.
Number one machine learning tool.
Yes, exactly. I think Excel is one of the most popular tools where a lot of OT teams and the plant managers do a lot of these things. So here the graph shows kind of like an elbow where you can look at, okay, what are the right frequencies? So for example, here for S2, you can see that probably like 1 every second might be good, because if you go to 2, it might be kind of less. So here you can look at it and then kind of figure out what is the right frequency of your sensors.
Makes sense.
Okay, so this would be sort of a longer term sort of process to say, okay, fine, once we change the frequency, you can go back to the process again.
Yep.
Anyway, so that's a side note. But let's look at, once we have those 15 sensors and now our data set, what can we do with it?
Yep.
So the first thing we typically do is what we call baseline modeling. So we are doing modeling, but we are creating a baseline, just looking at how are general algorithms behaving with this data. That's what we call the baseline algorithm. Now, the goal of this step is to figure out which algorithm is good for your data. That's what we want to do. Now, how do you know? I mean, if you're starting new, now how do you know which algorithm is good, right? You can just like Google it or whatever stuff. So I think one of the services that we have in Azure Machine Learning is automated ML, right? So this is like, think of it as it's a machine learning model to generate a machine learning model.
Okay.
Right? So you can give it a data set, which is our featured label data set that we cleaned up and everything's there. You can give it to it, and it will run through a lot of models that are relevant for that data set.
Okay.
Right? And it will run all the models, and then at the end, it will give you all the output that, okay, here are all the models that I ran. Here is the best model based on the metric that you gave me.
Yep.
And here is why it's the best model. So it will do all these things for you, right? So basically, this is the AutoML. You can provide this data set, and we started an experiment with some parameters, and then you run this experiment. And what you get at the end of it is something like this, right? So you would get this, which is, here are all the models that it ran.
Yep.
And for our sort of scenario, we used a different metric for precision, and I'll talk about that matrix a little bit later. And it will actually sort out and say, here are the algorithms, and here is the algorithm which seems to be producing the best sort of score. And when you click on explanation, it will actually tell you in this model, based on the predictions, what are the top sensors, which was one of our requirements to say, okay, which sensors are highly likely to affect my quality. So that's what I want to kind of figure out, right? So here it can tell me, here are the sensors, right? So here are the top 4, but let's say if I can kind of say, here are the top 10, right? So you can say S41, right? I abstracted the name of the sensor, but that's a sensor that's very highly affecting your quality.
Affecting or relevant in my measure of the quality, right?
Yeah, so it's correlated, right? Exactly. So it means that whenever either there is a positive or negative correlations, and that's what models are
the chances that there's an anomaly when that thing goes like that are higher. It's very high.
Exactly. Yeah. Compared to, let's say, S20 in this case, right? So that's what you're trying to figure out. And it can also provide you sort of like individual data point and kind of feature analysis and things like that you can look at the documentation. So that's the first step one. You go to AutoML, and this is kind of a very easy thing, right? Even if you're not a data scientist, you give your data set, it will just run through all the models and give you the model for you.
Exactly. Right? And that was a daunting part, which is like models. Like with these like fancy names of like people who invented them, we don't know who they are.
Yes.
You know, it's like philosophy almost. and so that's the part that ML on Azure takes care for you,
exactly.
Right?
And right now what I'm showing is I'm showing using the Python code that you can write. But let's say if you don't even know how to write Python code, you can do this all using just a user interface. So you can just do next. It's like a wizard. You upload your data, like if you have a CSV something, you upload your data, next, it runs the experiment and does everything for you as well.
Okay, nice.
Okay. So last step in the experiment, right, before we move, is, so we tried the AutoML where we looked at all the stuff, but let's say if you know a little bit of algorithms, you can also try a lot of these algorithms yourself. And so we have a sample around what are some of the common algorithms that people use for industrial IoT type data, right? Now, of course, there would be more. People would have preference to it. But here sort of like are the table. So most of them would be like decision trees because there is a lot of times data imbalance, right? Some data would be skewed and everything. So the decision trees generally are good algorithms overall. LGBM is the one that we're going to select for our model because LGBM stands for light gradient boosting mechanism. That's the algorithm. It will allow us to go and interpret or actually understand the model a little bit better, right? So that's the algorithm. That's open source. It's a really good algorithm. But anyway, so before we go out of the experiment and go to operate, right? We want to understand that what is the definition of a good model? How do you evaluate a model, right? Now there are a bunch of metrics that you can use, right? The most common one is the accuracy. How much times is the model accurately predicting thing? But that may be very aggregate sort of metric. A lot of times there are two metrics that generally people try to tune on. One is called precision, the other one is called recall, right? And so it's important to understand that for your business case, so in our case, we wanted to reduce the scrap. So if you want to go from 10% scrap to 5%, that 5% scrap right? What do I need to tune in my model? Right? Do I need to do precision, or do I need to tune recall? Like, or what do I need to tune in to get that 5% scrap? But that's an important thing. And so we have like a mapping, kind of very high level understanding of one approach to do that, right? So one would be you look at your existing business metrics, right? So for example, in our case would be how many quality failures are you receiving per shift, per batch, whatever. What's the percentage of scrap? This is one metric. What is the additional time that you need for quality rework or things like that, right? Or what is the cost of rework, right? And you can say, if the cost of rework is more, that's the metric I want to track, or things like that. Yeah? And then you tune your precision and recall in general, right? Now, like precision and recall are two kind of sides of a coin sometimes, because if you tune one, the other one could be affecting. But generally, this is the rule I tell people, right? If the cost of wrong prediction is very high, right? Let's say if you are based on your prediction, you're going to send someone, have a charter plane and go and fix something. You may want to make sure that you tune for precision. You want a precise prediction, otherwise your cost or prediction is wrong.
Yeah,
right?
That's interesting you're mentioning these points, because a couple of times I didn't interrupt you, but you need to have, once again, several people of different areas of the business work together on defining what's the best tuning for these models, where you're going to implement them, how, and so on. Because someone in your HR group might say, no, we can't hire 3 people. And so that's like basically you need to have the whole family, the entire village collaborate on that.
In fact, the data scientist, one of the requirements for data science projects that we do is to have a domain expert from the customer work with us, right? Because they know their data very well most of the times, and most manufacturers do have their domain experts, right? All they need is access to this latest tools, so they can upskill themselves and use all these things, right? So domain expertise is a very key important thing. It's a good point.
Nice.
And so that's how we kind of try to map out these things. So once you now figure out what are you going to tune for, precision, recall, things like that. Once you know what sensors you're going to use, right? And once you now know what algorithm you're going to use, you will be ready to build a model, right? So that's where you actually go and build the model. And this is the same process, and you register the model, right? So as we did for the data, we also need to register the model as well, so that you can actually use it for your later. So this is the model that we registered. This is the 4th version of it. Essentially, model is like a package file that you can now use for deployment anywhere. So that's where we graduate from the experiment phase, and now we go to the actual
operation.
So we graduate from the exploration phase and go to the experimentation phase. Right? So that's the exploration part. Okay. So now in the experimentation, as we talked about, one of the things is that these sensors that we selected may not be the only sensors. You may want to try with multiple sensors and try different things. Or you may also want to try with multiple different algorithms. Each algorithms have their own kind of parameters and everything. So you may want to try a bunch of these things. And so one of the important steps before you do experimentation is to figure out how are you going to create your automation out of it, right? How do you create a pipeline out of this, right? Because notebooks are good. You can write stuff manually in it. But at some point in time, you need to automate this whole process. So what you have done is for experimentation is converted these entire notebooks into automated pipelines. So we have 2 pipelines. We're going to talk about training, right? That's what experimentation is. And essentially pipelines are, think of it as they are multi-step, right? There are multiple steps. So you have step 1, step 2, step 3, things like that. Each step is just a Python code. You can copy paste the Python code from notebook and create a script out of it if you want. Or we also have a UI where you can drag and drop and create your pipelines as well, right? So similar to AutoML, you can do that as well. If you're not a Python person, just drag and drop stuff and you can create your pipeline.
Nice.
So in this scenario, I think what we are showing in the demo is copying the same notebook that we had and creating a pipeline. So we have 2 steps here: build the data sets and then build the model. Simple step. Right? You get the data, the process that I showed, where you merge the data, do all these things, and then you do that. Now the important thing here is that when you create your pipelines, you want to do 2 things. One is you want to parameterize your pipeline so that you can dynamically change the behavior of it. And you want to log, every time you run your pipeline, you want to log the stuff so that you can look back and see, debug stuff, what's going on, things like that. Now all these things is all part of the machine learning sort of SDK and tools that you provide. So if you use that, it's all kind of built in as part of it. But you want to just make sure that 2 things are there. So for our sort of experimentation here, we have 2 parameters. So one is the model name, and then the features that we want to use for our model. And then you can look at the different jobs that we have run. So for example, let's see if I can double click. Let's see. So if I go back here, and then look at our training pipeline and look at one of the training pipelines that we executed. You can also look at the logs that that come out of it, right? This is part of the outputs that are in there.
Okay.
But anyway, so this is a way of actually automating the entire sort of notebook experience and putting it as pipelines. At the end of the pipeline, what you should get is a model that's been sort of registered overall, right?
Okay.
So I think in the exploration part, all you're doing is you're just looking at all the algorithms, features, things like that. At the end of the experiment, when you run the experiment, you should get a model.
You should get a model, which is when we talk about running models at the edge and things like that. This is that binary that's going to be running, getting the real-time data through it and execute its thing to determine, predict that failures will happen or whatnot.
Yep, exactly. Yeah. So this is where the models kind of would come in here.
Got it.
And I think like the data set, you also want to make sure that you version your models as well, because your models will change and things like that. Okay. So once you have your pipeline, once you have your parameters and debugging, and you have your models registered, now your experiment phase is pretty much done. So now, because you now have a model that you're ready to test against the live data, right?
Okay.
So now you go from your experiment to your operate.
To your operation. Yeah. Cool. So we switch to operations. What are the things that need to be considered to switch to that operations phase? There's specifics to the industrial IoT that have to be taken into account.
Yeah, absolutely. Right. So I think, as we talked before, I think how are people? So at the end of the day, machine learning is helping plant managers or people in the factory make better decisions. It's a decision tool, right, at the end of the day. So we want to understand how the plant people and the manufacturers are making decisions, right? So for example, in scenarios where you are making a decision of whether to take an actual action in your manufacturing processes, you want to make sure that the action is done in a timely fashion, right? So you want to make sure that your operations, which is when you run your models and predictions, they are closer to that, right? Because if you have network connectivity issues or things like that, it might be a problem, right? But in scenarios where, let's say, you are doing, let's say, a 24-hour prediction, right, for the next day's inventory or something like that, or in our case, for example, we want to do the quality predictions, and generally it takes them 24 hours. For us, we are doing it every 15 minutes or something, right? We don't want to do it like real time because it doesn't help
add value
to it, right? So in our scenario, we can do that predictions in the cloud.
Okay.
So we don't have to push it on the edge. We can do it on the cloud as well. So those are the decision. The other important factor is how are you going to monitor your model's performance when it goes in the actual production. So when it starts predicting stuff, you also want to understand what is the model predicted and what was the actual, and then look at that as a comparison, and then figure out how your model is actually performing with the real world data, right? Because you trained your model using the historical past data. Now you want to make sure how your model is actually performing in real world data. And real world data is always messy sometimes, right?
And I assume this is when you would decide to eventually retrain the model with a new set of data and continuously optimize this model and eventually switch model and decide that, hey, at the end of the day, this is not the one I really wanted, but you still have to keep an eye on what's going on.
Yeah, exactly. So I think the example that I mentioned, let's say if you are optimizing for recall and your, let's say, threshold is 92% or something like that, and you look at your real world data and now you're just dropping from a 92 to, let's say, 85 or something. Now you need to go and retrain and say, how do I go back to 92, right? So that's kind of, that's a good important process.
Okay, well, Jomit, there was a lot. But actually, there was a lot of very valuable information that was easy to understand. So thanks for decrypting machine learning for us. So we have this samples repo, but you have other resources your team has been putting together. So can you tell us what is the next step for people watching this episode of the IoT Show? What you recommend they go do?
Yeah, sure. So there are two kind of resources which are key. So recently our team published the industrial IoT patterns in our architecture center. The goal for that was to look at the broad set of patterns across all different aspects of industrial IoT, not just machine learning, for example. And then the second is for specifically around machine learning, we have a GitHub repo, which actually has all the end-to-end samples that I showed here, all the notebooks, the code, some of the caveats around like what to do, things like that, right? So you can actually go and look at the GitHub repo, and it walks you through everything, right, from a sample, right? So all you need is an Azure subscription, for example. You can go and follow through the entire steps and replicate everything that we talked about.
Awesome. Perfect. So we'll bring up that link, aka.ms/IoT-samples. Jomit, you're welcome back on the IoT Show anytime to educate us on machine learning in industrial IoT scenarios, or others, actually, by the way. And well, to everyone who watched the episode, go have fun with machine learning now that you know everything you need to know about it. And hope to see you soon on the IoT Show. Bye.
Okay, bye.